Welcome to another video of RoboCNC. I'm Marcel. Today the second video in the Plasma Build series. So if you haven't seen the first one, please check the first one out and then come back to this one. In the first video we talked about what is plasma, how is it created, and what machine am I going to use to create the plasma. We talked a little bit about this torch, on which we will talk more later on, and this anti-coalition system with the sensors on it. I also told you that the first thing we needed to do is make this torch go up and down. This up and down motion is the Z-axis in my case, in most cases, but I'm gonna call it the Z-axis, up and down travel of this torch. And there are a couple of features needed in this Z-axis. So first let me take you into the CAD Design, the computer-aided design, and have a small look over there before we're going to build it in real life. So here we are in Autodesk Fusion, which I use to create or design the machine. It's the computer-aided design. We here see the Z-axis, and as I'm planning to make it. Some parts are still missing, but we'll see those later on. It seems to be a bit of a beefy Z-axis, which is correct, because I, in an ideal world, hope to also be able to place a spindle on here when I take the torch off. Anyway, we started in the first video with this machine torch and the Z-axis anti-coalition system, and now we see we have some strange motion going on here in this Z-axis, which I'm going to explain you later on. But first we need to machine some of these aluminum parts. So let's hop into the workshop. So the aluminum parts are ready. I'm starting the assembly, and if you want to skip over to the assembly you can do so due to the magic of video editing, because this video is chapterized. If you, on the other hand, want to know how I made these aluminum parts on the CNC router that we built in another video series, you can see over here that I made some small footage on the machining. So let's go. So for those new here, this is the RoboCNC X2 router. The complete build of this router is also on YouTube, so check it out on my YouTube channel and make sure to subscribe. In one of the last videos I made this new spoil board, and the spoil board is to give me a really flat surface that the tape can stick to. The sticky tape method that I'm using here is not my idea. I found it on YouTube on Stony CNC, and I really love this method. It's working absolutely amazing. So you put the glue on one side, put the activator on the other side, align the part with some bolts, push it together, and it's tight. Really, it's hold on there firm. So I take the remaining tape off to prevent cooling from getting under the part due to capillary effect. So now it's time for machining, and I have no clamps to worry about while machining, which is absolutely fabulous. So I made this strategy with Fusion CAM, computer aided manufacturing, and it's the 2D adaptive strategy to prevent having to have a full width of cut. So the machining that I do here is done on the RoboCNC X2 router. Make sure to follow that complete build, which is on our YouTube channel, including all the drawings that you can get there for free. So make sure to check it out. It was pretty cool to do. You see me machining, and you see a mist coolant system, and this mist coolant system is the fog buster, which I have a complete video on somewhere else on the YouTube channel. And the coolant used is an IPA alcohol, so it gets really cold and it evaporates quickly without having residue on the part.
So when the machining is done, you can break the tape bond and take the tape off, and you're ready to go. After doing machining in aluminum, I love to get some dull finish in the sandblaster, and there's no sand in here. It's glass bead, and the glass bead do not ruin the dimensional properties of the part, but they give it a dull finish with just some micro dents in the surface. In the description below the video you can find all the tools that I use. I will use some affiliate links to help you find the right tool, and you will help me keep this channel going. So now it's finally time for assembly of the Z-axis. What you see here is the back plate, basically the backbone of the complete Z-axis, and on the sides are some spacers. These pins are 8mm precision dowel pins, and they will make sure that those spacers can only be placed on there straight and exactly parallel to each other. Now, since we're going to use quite a big ball screw, a 25mm ball screw, I need those spacers between the linear rails and the back plate to give me some more space between the back and the front plate. So the rails that I will be using is the HIWIN brand, and I got them from CNC. These HIWIN rails have an arrow on them pointing to the reference side, and although it's not all that necessary for this application, I tend to always put the reference side to one side. In this case it's pointing to the left. So the rails are placed and the bolts are hand tight. Now it's time for the 25mm bearing blocks themselves. So again, these bearing blocks are not symmetrical completely. You see one shiny surface and one dull surface on the side. So the shiny surface again is the reference side, so not this side, but this side is going to point to the left. There's a little plastic ball retainer in there to make sure that the balls of the bearing do not fall out. So push it against the rail, slide the bearing on the rail, and then you have the plastic part. So now it's time to align the HIWIN rail to the left side of the back plate. So the left side of the back plate will be my reference. I use a magnetic dial indicator to align the left rail to the left side of the back plate. So when I was happy with the left rail and it was parallel to the left side of the back plate, it's time to align the right rail. So I put the magnetic base on top of that and I reference to the left rail. Now the last part of the alignment puzzle for now are these heavy duty slotted spring type straight pins. The linear rails are on the back plate with some spacers, and the reason for that is that I'm going to use quite a big ball screw. So this ball screw is 25mm with a 25mm ball nut. Is that needed for a plasma? No, it is
for sure not needed for a plasma table, but as I told you before, in the ideal world I might use this Z-axis also for a spindle, like a router spindle, and in that case I would opt for a bigger Z-axis, and so let's just make it big. A ball nut and a ball screw have to come together, and I've seen colleagues of mine, I will not call them by name, but I've seen them taking this off a ball screw, and afterwards they are on their knees finding all the little balls that are inside here. So if you want to do that, make sure to have a plastic ball retainer, just like with the bearing blocks from HIWIN. I use the same technique. By using a piece of plastic to keep the balls inside here. So, now this size makes the need for the spacers. It will go in here, but to mount this all I have some SYK parts from Taiwan. I didn't order these from Taiwan SYK, I ordered them from CNC. And this is not a sponsored video, but just, I mean, the ball screw, the ball nut, the end machining of this ball nut, ball screw to accommodate with the bearing blocks from SYK. The SYK bearing blocks and all the parts needed to assemble this Z-axis, it's just a one stop and go. I go to CNC, put it all in my basket, put the money in, and then start building. I mean, they're not the cheapest shop around, but they do sell some high quality stuff, so absolutely recommend them. Okay, so for now, we've seen these before, and truth is, last time I bought these from AliExpress and they were, I'm not sure if they are the same quality, but it worked fine. But again, now they come from CNC. And the parts and the links will be down in the description box below. Okay, so now we see where those alignment pins, the slotted pins, come into play. So this bracket, the MBA15F from SYK, is going to hold the NEMA 34 motor on the top side. On the bottom side it's going to hold the FK15 fixed bearing for the spindle, and here in the middle there is some room for a coupler. Now this bearing, FK15, perfectly fits in here. So inside here is a double rode angular contact bearing, if I remember correctly, and that takes up the radial loads like a normal bearing. So because it's spinning, it has some radial loads, and that's been taken up by this bearing. It's supported by this bearing, but also the axial loads. So this
spindle is going to push down and upwards, and especially when there's a router, a spindle on the z-axis, there will be a lot of axial loads, and that will be taken up by this bearing. As CNC told me, there are a lot of clones of this bearing. You can buy these Chinese for a lot cheaper, but this is a C3 quality, and that's not comparable with the C7, for instance, or whatever you get from AliExpress. Anyway, I will fix this now to the bracket. So the last SYK part is this ball nut bracket. This bracket will convert the round formed ball nut bracket to a square one. To be honest, this is a bit beefy for my application, but it's not that expensive, and machining it myself, well. So let's put this on here. Directional. On one side fits the bolt ahead to make it flush, and on this side the bolt sticks out. And now you can probably also see what these big holes are for, so that I can mount these bolts. So last thing to do, fit this inside the bearing. These two little parts came with the bearing, a ring which goes on, and a locking nut. Bearing blocks come with a grease nipple, which I will put on later. I will put the reference side up to the left side, push them on, and always keep these, they come in handy. This thing is starting to look like a Z-axis. So due to a battery failure, you missed out on the most satisfying part, and that is putting the green caps in. I'm sorry. You will have to subscribe to another YouTube channel to see that. Well, now the next aluminum plate, and this one is the front plate, but it's the driven one. I will explain that later on. this aluminum plate is now on the top row of the HIWIN blocks, and this is the plate that will be driven by the ball nut, or by the ball screw with the ball nut with the bracket. Now I have to turn this over and put these bolts through the bracket inside the plate. But since these are stainless bolts and the plate is aluminum, but since these are stainless bolts and the plate is aluminum, which I do not recommend, but why do I do it then? Because I had these laying around. Use some anti-seize. So, putting on a bit of anti-seize, because really stainless steel will seize itself in aluminum. Don't be as stupid as I am by putting these in. So in theory, the blocks, the bearing blocks should have been exactly the same height as the bracket that retains the ball nut. But in reality, there was too much friction. So I had to use thin sheet of copper to give it a little bit of extra space. And I didn't manage to film that, because I was crying, of course. So anyway, this is really starting to look like a Z-axis. Now, I will explain it in more detail, but this plate with the nice engraving should be mounted on top of this one, and then it should slide just in front of this plate. So if you manage to get that right, then you're fine, and otherwise you will have to shim this a little bit so there's no friction between this plate and this plate. So I will now mount this and we will see, and otherwise I will shim it again. Ooh. Almost lost my bearings. Again, stainless steel bolts, because I had them laying around. In aluminum, use anti-seize. I really don't use stainless steel bolts, basically, in aluminum. And if you have to, maybe someone in the comments can explain why stainless steel and aluminum seize up. Could be interesting. So it's not completely smooth, so I am going to shim it. So now it's smooth. Okay. A small little recap. This is the top bearing plate. And the top bearing plate is going to be driven by the complete motor assembly of the Z-axis. On the bottom here we see the bottom bearing plate, which is floating. This one can freely move. Mounted on the floating bearing plate is the front plate, and this front plate needs to be fixed somehow to this top plate. So if I slide it up there, I could bolt it down when I'm going to use a spindle motor, but for now I'm going to use two of these little springs and two of these little set screws. Let me bring you in a little bit closer. These bearing blocks can hold a grease nipple on either the upper side or the lower side. So I'm going to leave the screw that closes it off in between the two bearing plates and place this tiny little spring exactly on top of it. And it's a really snug fit. Now with both springs in place, I'm gonna slide this up. And lay it down. Now I'm gonna take one of these little set screws and put them in these oval shaped holes. So this oval shaped hole will make sure I have still got the play in the up and down motion. But first I'm gonna take a little bit of Loctite 242, a bit of thread locker to secure this in the aluminum plate. So the little bracket I just placed on there is to hold the anti-coalition system you saw in video 1. On the top you saw a little microswitch that is triggered against the spring tension. I will do a separate video on explaining all that stuff in more detail and also telling more about the different options you have there, but know that the torch that is going to cut the material needs to know where the material is. So now it can travel down, this plate goes up against the spring tension, triggers the little switch, and now the plasma torch knows where the material is that it needs to cut. Next step is the motor, and there are a lot of options when choosing a motor. We already know it's going to be NEMA 34, but let's do a separate video on that. I hope you liked the video. Thumbs up if you did. Also make sure to subscribe and if you haven't done already, click the bell to get notified for the next video. Thanks for watching and hope to see you next time.